right, and with that, we are ready to get started here. Okay, so this will be a session which will provide an introduction to machine learning. So this will be, there are many ways to introduce the topic. So my assumption is that all of you here in the room have maybe heard about machine learning, read many papers that use machine learning, but haven't in practice used machine learning methods yourselves. And there are many ways to teach machine learning. Some of them will be a little bit more theoretical and involve more writing out math and equations and things like that. In the spirit of Neuroacademy, this introduction will have a little bit of math, but mostly we'll focus on code. And so we'll try to boil this down to practice in, and I'll talk a lot about principles, and there'll be some theory here as well, and kind of big picture of how we do machine learning. But I'll try to boil this down to practice in data and code using some Jupyter notebooks that I've inherited from Talia Arconi, who deserves a lot of the credit for writing this. And we'll look at some neuroimaging data as an example for the kinds of things that people do when we use machine learning methods in neuroimaging data analysis. So with that, well, here's some preliminaries. We don't need to talk too much about that. All of the software, this is written to be used maybe by others as well. So there's a lot of here in this. So I should say we're in the curriculum and Rochem-ML, you can follow along in the hub as well. And this preliminary notebook will introduce first kind of the data set that we will work with, and then we will go and we'll talk about machine learning more broadly. So the data set that we will work with is an open neuroimaging data set called the Autism Brain Imaging Data Exchange 2 data set. So ABIDE 2. It's the second round of this very big project that involved data collection from individuals with autism and healthy controls in multiple different locations, multiple different scanners. We are going to use data that has been already processed and appears in a TSV file. And I think maybe many of you have seen now pandas in action. And so the next few lines of code won't be too mysterious. We're going to import pandas as PD here and use the read CSV function in order to read a TSV file. This is a tab separated value file, and we're telling pandas that there are tabs in there so that it knows to use tabs as separators and not commas, as you might expect from the C and CSV. So this is the data set that we're using. So in each row in this data set, in this table, there's one individual from this ABIDE data set. And you can see the first column is the site in which this was collected. So they're all ABIDE 2 data sets, and then there's like various things. OHSU is the Oregon Health Sciences University in Portland, NYU is New York University, and so on and so forth. So each individual is collected in different sites. There's an identifier. There's their age up to a ridiculous amount of precision. There's something called age resid. We'll come back to that later. There's sex. That is coded as 2 and 1, and I never really remember which is which here. And group, which is also coded as 1 and 2, and I also never really remember which is which, but there are different groups and there are different sexes. And then there's, so these will think of these as kind of like the phenotypical data, the phenotypes of these individuals. And then there's a bunch of columns here labeled as FS something, and that's because the data are T1 weighted MRIs that were processed with FreeSurfer, and then from this FreeSurfer, the values were derived for a variety of different ROIs, including surface area, cortical thickness, and a couple of other things that I don't remember as well. But there's multiple of these MRI measurements. So we're talking about a data set that has here we're seeing only 5 rows, but the data set shape overall is 1,004 rows. By 440 columns. So in fact, there are 1,004 subjects here, each row for each subject. And then there are, subtracting these 6 first columns, there are 1,440 features, we call them, or kind of like measurements per individual. And this, of course, after we've reduced the data enormously, right? And T1 weighted MRI contains a lot of dimensions because you can think of each voxel as a separate dimension. But now we've reduced this down to merely 1,440 dimensions. And this introduces kind of, to me, sort of demonstrates one of the purposes of machine learning, and something that I hope that we will kind of get to over the course of this next hour and a half, which is data that we deal with is often very, very high dimensional. We call this very high dimensional. We think of each one of these as a dimension. It's very large. It can be very large in the number of rows, but very, very often we deal with situations where we have a lot more columns, a lot more features to work with than individual subjects in the data set. And that poses a lot of different problems. We'll see those in action. Those the kind of problems we run into in just a little bit here. But I thought I'd sort of point to that first, because that's something that should be top of mind for us as we're thinking about machine learning. Okay. So having introduced the data set that we will work with, let's back off a little bit and introduce just the general idea of machine learning. The notebooks here kind of have a lot of commenting, and I'll go pretty quickly through these first few things. Here we're loading some things that we'll need along the way in order to demonstrate things. So, okay, what is machine learning? This might be a good point at which to provide some definition. So machine learning, one definition that we can use is that machine learning is the field of science and engineering that seeks to build systems that are capable of learning from experience. So machine learning, you can think of it as a subset of a larger field that we think of as artificial intelligence. This is the field of science and engineering that seeks to build systems that can independently do sophisticated operations on our behalf. And one approach to that is to take a system and encode into it, say, a decision tree. You're faced with this following thing, you should do the following other thing, kind of like building in the algorithms of its operation. That's kind of one field, and this was a field that was very popular maybe about 35 years ago, called expert systems, where people built these kind of systems that encode explicit rules. Machine learning goes in a different direction. You could think of it as adopting into AI principles from statistics, which is the idea that if we observe data in the world, then we can build systems that learn from observation of the data. We can build models that encode their observations of the data into parameters of the model in such a way that when faced with new data, faced with new observations from the world, they can make inferences about the data. And we'll see what could be the purpose of these inferences in the context of statistics as traditionally used in psychology and similar fields. Statistical inference refers often to kind of figuring out which of a bunch of parameters or which of a bunch of variables is meaningfully or statistically significant in inferring something about dependent variables. Typically, when we do statistics, we have a dependent variable. Let's say in this data set, that might be the age of the individuals. And then we have a bunch of independent variables. In this case, this might be the brain measurements. And we might ask questions like, which one of these independent variables statistically significantly kind of varies with the dependent variable. So, machine learning takes a slightly different tack on this, and this will be something that we'll see here, and is really kind of at the core of machine learning, is that it seeks to invert this a little bit in the sense that instead of looking at these independent variables and selecting from among them the meaningful ones or the ones that statistically significantly relate, we're trying to do some operation by which we will learn a good model such that the prediction of the dependent variable, the age of the individual, say, is accurate. Now, prediction and explanation of this kind, as written here, are not mutually exclusive. You can do well with both of these things, but it's worth thinking about these things as sort of different and maybe independent kinds of goals of statistics, of machine learning, and thinking about what do we get when we do those various things. There's some links here to some papers if you must read one paper that discusses this distinction between machine learning and traditional inference in psychology, I recommend Tal Yarkoni and Jake Westfall's paper from 2017 that has machine learning in its title and is a really good read if your training is mostly in the kind of statistics we do, say in psychology or kind of adjacent fields, biology. Really also a pleasant read as well. And there are some others that are more statistically minded. Let me see if I can find one in particular that I wanted to point out, just because I just learned that the author of that just received this really fancy, basically the Nobel of Statistics. Never mind, I can't find it, but I will post later about this Slack. Okay. So having said that, those kind of very general words, let's talk about what we do in machine learning. So you can talk about machine learning doing a variety of different tasks under different conditions. The main distinction that we make in machine learning is between supervised and unsupervised learning. It's easier to explain supervised learning, so I'll start with that. And that's the setting that I already sort of described, where we have a bunch of independent variables like measurements of brain structure and a dependent variable like age, and we try to infer the dependent variable from these independent variables. So for example, predicting people's chronological age from structural brain differences, or under some conditions that may be something like, oh, we have a label for every observation, whether it's in spam or not spam, and we're trying to learn which is which, or predicting a person's rating of a particular movie based on their ratings of other movies, given that we have a lot of data where a lot of people rated various movies, and we know other characteristics of these movies, like how long they are, whether they're a comedy or not, and things of that sort. Another kind of way in which we can think about supervised learning is things like diagnosing schizophrenia based on genetic markers, and that's sort of a lot of clinically oriented machine learning research comes under this flavor of supervised learning. So in supervised learning, we have what we think of as the features. We conventionally label these as capital X, and a vector of labels or observations. That's what I so far have referred to as the dependent variable y, so designated as lowercase y. And this will typically be a matrix. It'll have a number of rows that is similar to, well, the number of observations, subjects in kind of the setting of the abide, and it has a number of columns that in this case is 1440, which is kind of like how many regions have we quantified different things for. And then y will typically be a column vector with the number of rows being the number of subjects. So we have an age for every subject in this data set. Okay, within supervised learning, we can further subdivide the kinds of tasks that we can do into things like classification versus regression. So we'll start again with the one that's easier to describe, which is regression. Regression is the operation by which, and it's very similar to linear regression that you've seen in other contexts, is if we have, in this case, we have, I think 30 observations here, and they're just randomly selected or randomly generated here. And we can think of this as being a very simple data set where there's one feature. So X is the one feature and Y is, say, the outcome or the label. And in this case, we're trying to determine in regression, we're trying to, Y is a continuous variable, and we're trying to determine, given an input X, what is the output Y? So we're trying to build a model or parameterize a model that for a given X will give us some guess of Y. And we want that guess to be as good as possible. One way to solve this problem is called ordinary least squares regression. In this case, we're fitting a straight line that goes through this. This has two parameters, the offset of the line or the intercept and the slope of the line. This is maybe almost the simplest possible machine learning model you can can imagine. So here it's estimated 2 parameters for a very particular structure. This particular structure is, we'll have, let's see if the equation is written here. Yeah, y hat, which is our guess of y, equals to some intercept negative 0.37 plus some slope times x, 0.62 times x. That's linear regression. So here we've solved it using a particular kind of approach, but you can imagine in any other or many other kinds of equations that are not like this, but other kinds of equations that we can fit kind of parameterize using the data in order to learn the relationship between x. So that's regression when the output is a continuous variable. Classification, on the other hand, is the case where the individual observations are identified as belonging to different discrete classes. So here there's yellow points and the blue points. In this case, the x, the features it's actually 2-dimensional. So each one of these has an x1, which is sort of the horizontal here, and an x2, which is the vertical here. And we can see that they're clearly separated in this case. So you can imagine some kind of model where we determine based on a value of x1 and x2, the horizontal and vertical location of each one of these, which class it belongs to. One thing you could do is draw a straight line in between here and say, if you're on one side of the line, you're yellow. If you're on the other side, you're blue. That could be a classification rule. I won't show this here. I'll come back to classification a little bit later. So that's what that might look like. In this case, it's really easy, but in many cases, the data looks a lot more like this, in which case you need to determine how to do this. They're intermingled. So it's not as easy. And, as written down here, there might not be a perfect way to do this, but there's a kind of like you can come up with some rule where maybe you want to find as many of the blue ones as possible, right? Maybe finding blue dots is really important in this case, in which case you maybe put the line right up here above all the blue dots, and maybe you don't care so much about including some yellows in there. So depending on what you're doing here, this might be a good way to do that. This putting the line up here seems to be what my Gmail spam algorithm seems to do, as it seems to send my NIH program officers emails to my spam box on a regular basis, which why? Really, any email that had an NIH.gov goes straight to spam for some reason. Very useful for someone in biomedical research. At any rate, that could be a rule. So that's classification. This is another kind of, could be another kind of classification problem. Here, there are several different classes. These are still discrete classes. So each color here is a discrete class. And maybe we're trying to determine the class of each one of these. Okay, so I'll stop here. What questions do you have so far about just the setting, supervised versus unsupervised, regression versus classification?
I have a question.
Yeah, go ahead.
When you're talking about regression here, the example you showed was linear, but you mean that could be any type of model fitting, right? That's what regression means versus classification is like separating into groups.
Yeah, that's exactly right. Yes,
Okay.
and we'll see very shortly. We'll see models that are not the linear regression, but are other nonlinear regression kinds of things. So that will become a little bit more concrete in just a few minutes.
Yeah, I was actually going to ask something quite similar, that in the case of, say, logistic regression, where we've got a binary or any category outcome really, that's still regression, not classification, right?
Yeah.
Or would that count as classification actually?
Because
you're still regressing factors out.
Yeah, I would think of logistic regression being actually an algorithm or a model whose purpose is to perform classification, right? But
Right,
it kind of
okay.
Depends a little bit on how you read out the outputs, right? There are two ways to read out the output of a logistic regression algorithm. One is the probability that it belongs to one class versus another, which is a continuous variable. And the other is a readout when you say, oh, if it's above 0.5, I'll just call it category 1. If it's below 0.5, I'll just call it category 0. So it depends a little bit on the output or how you read out the output. So that's just to say the distinction between classification and regression is not all that hard and fast. It's easy to think about these two tasks and two kinds of tasks that we might eventually do with, say, with this kind of brain data. So it helps kind of talk about things, but it's not necessarily kind of like a hard and fast boundary between these.
Thank you.
Great. Yes.
Is the parallel between supervised and unsupervised learning similar to like confirmatory versus an exploratory analysis, like in a piece of analogy?
Maybe. I'm not 100% sure that I know. Kind of like, yeah, I think confirmatory and exploratory is more about like the knowledge, the pre-knowledge that you come with, and this is not so much. This is about what data you have.
Okay, like
available
more
to you.
methodological.
Yeah, I think it's more less conceptually. Yeah. Okay, so with that, I will talk about unsupervised learning a little bit. So in the supervised learning setting, and again, these distinctions are not like hard and fast, but it helps to set things in some framework to say, typically in the supervised learning setting, we have this kind of outcome that is a very clear, one of our variables is clearly an outcome, like the age of the individuals or their diagnosis, right? Whether or not they're diagnosed, have an autism diagnosis. But in many cases, we don't have that. Imagine that we only had a bunch of people and brain measurements from all of these people, and we didn't know much about them, or maybe we're only looking at their brain measurements, and we're interested in sort of understanding the structure of this multivariate data set that we're faced with. In that case, what we might be doing is something that's more like unsupervised learning. So one form, and there's sort of you can see maybe parallels between the different kinds of supervised learning and different kinds of unsupervised learning. One approach here is to perform clustering. In clustering, we take some data, for example, here's some data, and we look at it. And so this is very similar to our sort of classification data, but there are no labels associated with this. Instead, the data is distributed. In this case, this is data. Again, each point has two variables, two features associated with it, kind of like our X1 and our X2 on the horizontal and vertical axes. And we look in this data and we say, well, there seems to be some structure here. This seems to break down into various clusters, right? There are clusters of points. This is a very contrived example, of course, where, it's very clear there's this thing up here, this thing down here, this thing down here. And so in this case, maybe we assign colors. So in this case, this is not that we had some pre-knowledge of these colors. Instead, through the process of machine learning, we assign colors to each of these things and cluster them. And you can think of various cases where you want to take a data set and break it apart into natural kinds or into different groups based on the structure of the multivariate data that you have. Right. So, but again, in the real world, often maybe there are natural kinds, but what we see is something like this, and this is a whole lot harder to cluster than this. So this again worth keeping in mind when you think about clustering, that this is it's very evident what you need to do here. But when you're faced with something like this, it's not as evident. If your goal is to cluster the data into groups in some way, it can be pretty. Okay, so that's clustering. The other kind of unsupervised learning that we think about is dimensionality reduction. I'll show again, pretty contrived example of dimensionality reduction. So again, this is a data set that has two variables. Each point here is defined according to its distance along the horizontal dimension, distance along the vertical dimension. And the purpose of dimensionality reduction is to take something, in this case, that has two dimensions and reduce its dimensionality. Think about in 2 dimensions, it's very easy to plot this thing, but often the data that we deal with for example, the 1440 dimensions, it's just very hard to deal with all that dimensionality for a variety of reasons, some of which we'll see in just a few minutes. And it could be a good idea to try to squeeze out some dimensions. What do I mean by squeeze out some dimensions? I mean that if you look at this data, it's clear that there's a lot of variance along some directions here and very little variance along other directions. And so if you were to decide, okay, instead of describing each point as two numbers, its distance along the horizontal and its distance along the vertical, I would choose just one number, which is the distance from the bottom right or bottom left corner of the plot. Just how far do I need to go along this diagonal? You wouldn't lose a lot from doing that. And that's the main sort of idea behind dimensionality reduction. Let's take data that has two dimensions, describe it only in one dimension, and see that we didn't lose all that much information. That's because in this case, X1 and X2 are very highly correlated with each other. So if I know X1, I know a lot about X2. And a different way to describe each point here is by saying, well, how far are we along this diagonal? So that's dimensionality reduction. So now we've sort of drawn the full tree, and there are combinations, there are all kinds of subtleties around these things, but broadly speaking, machine learning divides into supervised, unsupervised, regression, classification, clustering, dimensionality reduction, and combinations of these things.
Can I ask another question?
Yes.
Yeah, I have a question about clustering. Is there a way to kind of like perform supervised clustering where you're still expecting to be able to limit the amount of clusters that you observe? Like a mixture between clustering and classification?
Yeah, I won't go into much into this, but clustering is a bit of, among all these, clustering is the one that most like an art rather than a science, because you have to put into it all kinds of knowledge, like how many clusters do I expect there to be here, and you have to do a lot more fiddling than most of these methods. So we won't talk much about clustering in any of this tutorial, but clustering is the one that's a little fiddly, and there are combinations, like I said, there are combinations of these different methods, like, first do dimensionality reduction and then follow that with some other operation after you've reduced the dimensionality, things like that. Did that answer your question? I'm not sure.
Yeah, thank you.
Okay, what other questions? All right, let's get into it then. Okay, so now I have this data set. I've showed it to you before, and I've read it into the memory in this. And now I'm going to introduce the kind of workhorse of machine learning in Python, which is the scikit-learn package. Scikit-learn is a really great software library. It's been around for a while now, and it's like very, very mature software library, very highly adopted across both uses in scientific research, but also very widely used in data science and industry, and just kind of like a standard of how to do machine learning in Python. One of its really great features is that it has amazing documentation. So let's see, I know how to find scikit-learn. So if you go to the scikit-learn.org website, you can read this website really almost like a textbook for applied machine learning. There are numerous examples of a variety of different approaches. It's really, really great. So I'll just point to that and then go back here. So data in scikit-learn is represented using NumPy arrays. Here, for example, I'm going to read. So here I'm filtering the data that I had before, this table of data. I'm filtering using pandas filter, and I'm restricting it only to the columns that start with FS, and those are the columns that contain the brain data. So here's the table. Excuse me. And here I'm going to select the age column and put the values of the age into a column Y. So we have a NumPy array called Y that contains the ages, and then we have it's not a NumPy array, actually, it's a pandas data frame that has the values of all these ROIs and kind of like these features of the brain. And what I like to do here as a demonstration is to sample from the columns of Excel. I'm going to sample 5 columns at random. And I have already my my Y, but I'll do that again here just for clarity. And then what I'm going to do is I'm going to use scikit-learn in order to perform a linear regression between Y and these 5 features. So I've reduced this down. X here is now only 5 columns. And the following code will show what scikit-learn, or how you use scikit-learn in order to fit. So from scikit-learn, or as it's shortened in code, sklearn, in the sub module of scikit-learn called linear model, there is an object called linear regression. And linear regression is one of a family of what are called in scikit-learn estimators. There's a variety of estimators. We'll see a lot of different, or a few different estimators here. This is the first estimator that we're seeing. The estimators can be initialized. So it's a linear regression is a Python class. In order to instantiate an instance of the class linear regression, we call its initializer, in this case, with empty parentheses. So this is a call to a function that's attached to this class that initializes an instance of this class. Here it is. This is the way we present these in the Jupyter notebook. It's I don't know, type. It's a type linear regression object. It's an object. It has methods associated with it that we can start using next. Notice no data has been observed yet. So we start by initializing an object that has the notion of a linear regression associated with it. It has all the machinery in it in order to fit linear regressions once it sees some data. And that's what's happening here next. So now we pass to it X and Y, and we pass it to a method called fit. And it is only once we pass this model.fit, I wonder if the change in color here is related to the fact that now it's seen data and now it's learned about the world, and it has determined its coefficients. So here are the coefficients, or the parameters of the linear regression model, because it's got because it has 5 features. There are 5 coefficients, and separately also an intercept associated with that. So it's similar to the linear regression you saw before, but instead of having Y equals something plus, or beta 0 plus beta 1 x1, now we have Y equals beta 0 plus beta 1 x1 plus beta 2 x2 plus beta 3 x3. Do I have the equation down here? It is down here, this equation, right? So we learned these parameters for this kind of structure of the problem. We have 5 input parameters and or 5 input columns, and then we have 6 parameters associated with that. So it's a linear regression, but in 5 dimensions instead of 1. Now notice that in scikit-learn, now there's this model. I should point out, when I initialize this model initially, if I try to do intercept underscore, it will say, sorry, I don't have an attribute intercept. These attributes intercept underscore and coef underscore only get populated when the model has seen some data. And this is a convention across all of scikit-learn that attributes of these estimator objects that have an underscore at the end of their name are attributes that get allocated only when the model sees some data. So in its pre-data shape or form, when we initialized it here and didn't give it data yet, it doesn't know what the intercept is. But once it's been fit, now it knows the intercept. Okay, so we fit this with some data. We have these parameters. The next thing that we can turn around and do is we can use this model in order to make a prediction. You remember when I started, I said machine learning is really distinct from traditional statistical inference because we will be obsessed with prediction, with predicting variables. So here we're predicting the values of Y. we've given it the same x's, and we're saying, given this set of equations, if I gave you all these x's, what would you predict based on this should y be? And we can sort of show what that looks like. So we have the age predicted, this y pred on the x-axis here, and the true age on the y-axis here, and this is the result, this is the prediction of the model. So, you know, it's, I don't know, it is what it is. We can talk about how we quantify that in just a minute, but we'll see there's some kind of, the predicted age is within some range, the true age is within a different range, so, you know, it's captured something, but maybe not everything. So here's just all of the code in one cell, just to show you how simple this is. So you initialize a model, you fit it, and then you generate predictions. So in 3 lines of code, you get kind of a prediction already from a model that you've learned. Here's another thing you could do, which is use stats models in order to fit a model and get p-values about which variables and so on and so forth. That's not what we're doing here. So we'll just get past that and say, well, how do we know whether this model is good or not? So I'll go forward with that, and then I'll take questions after that about everything that I've shown so far. One way to determine whether the model is good is to compare the predictions to the true values using something called the coefficient of determination. The coefficient of determination, capital R squared, is a way to quantify the proportion of variance that is explained by the predicted value. So here in this case, for example, I looked at this and I said, I don't know, is it good, is it not good? Here's a number that I got associated, a quantitative metric, 20% variance explained by the predictions in the true values. So you can decide for yourself, depending on the problem, is this good, is this bad, is this like what to do with this? Certainly it's not as accurate as asking people what their age is, but if all you have is their brain measurement, maybe 20% variance explained is really good. So again, it's a little subjective and very dependent on your particulars, whatever this is good about. So okay, so this is ultimately, we'll use this number, this coefficient of determination. Coefficient of determination is a very common one for regression problems. Again, this is a regression problem, one that you'll see very often used. Okay, let me stop here. What questions do you have so far about scikit-learn, these mechanics, coefficient of determination?
I would ask another one if you don't mind. Don't want to be taking up too much space.
Yeah, go ahead. And then
Yeah, sorry. I'm just wondering again, just talking about the way Python is maybe different from, say, R, with the way we import different packages. Outside of the scikit-learn environment, is it possible to run these models like in native Python or just using another package?
Oh, I mean, you mean outside of Jupyter?
No, outside of scikit-learn, actually,
Yeah,
without
no.
the.
In the way that this code appears here, it really depends on scikit-learn. Like this
Right.
object that's initialized here is implemented in the scikit-learn library, and you have to have installed scikit-learn and imported it from scikit-learn. It's not in the base language at all. Python, the base Python has very little math, and definitely almost no statistics at all. So Python is kind of built on this kind of composing your environment out of these additional packages that you install. And that's quite different from R that comes very, very full-featured.
Yeah.
You had a question?
How would you speak about the relationship between machine learning and Bayesian statistics?
Between machine learning and?
Bayesian statistics?
It's a little complicated. Often, if your goal, like the way that we think about machine learning is we're going to be very, very adamant that what we want is accurate predictions. And often the Bayesian logic is a really good one to use if what you really want is accurate predictions. For example, taking into account the priors on, I don't know, the distribution of age in your population is maybe very useful in designing these models. So you can incorporate Bayesian logic into a machine learning algorithm or not, depending on how you think about this. I'll show something in a little while that we'll come back to this notion of priors. So we'll come back to priors and kind of Bayesian thinking a lot later. Not that much later because we don't have that much time, but in a bit. And so, okay, well, let me actually just see. But yes.
Is this, if you wanted to just do the linear regression outside of machine learning, is this the path which you would want to use, or is it better?
So stats models will give you a lot more
Oh, sorry.
stats. I skipped really quickly through this, but stats models is like more like the R LM, I guess, right? Or even LME4, all those. You could do linear mixed effects and so on. So I'm just pointing to stats models here because it is really useful, but that's not what we're doing here. And this is just an example. You get a lot more like things like, you know, these kind of standard things, p-values and confidence intervals and all kinds of Durbin-Watson things and so on. So that's stats models. So this, you know, if you want parametric statistics, stats models is your thing. Okay, so here is actually, I showed you very concise 3 lines of code to kind of initialize, fit, and predict. Here's even faster to get to, what's going on? Oh, I went back here and that did that. Even faster to get to the score, right? So each one of these estimators has a scoring or score method. If you give it X and Y, it will fit, predict, and give you the score. So if all you're interested in is how well does a linear regression predict age in this data set, you can get that in 3 lines of code. Yeah, no, 3 lines of code. This doesn't actually fit and predict. It just scores on, and this could be the data that you used in order to fit. It can be some other data, and that's going to become really important soon. Okay, I'm going to actually skip over this classification thing, but there's a bunch of classification stuff down here. In the interest of time, I'm going to go straight to more conceptual stuff here. Okay, so we've used scikit-learn's linear model now in order to fit, and we've kind of emphasized this focus on model prediction error. Let's look at some potential challenges to this paradigm. Here I'm creating a function, and that function creates some data. Here's some data. Okay, so this is again a relatively simple case. Y is the one output variable, and there's one input variable or your X. If you look closely at this, you'll see that Y is generated using second order polynomial in this case with some added noise. And so if we fit a linear regression model to this data, it's not going to do so great. And here's some error. Error, by the way, error and R squared are going to be closely related to each other. So calculating mean squared error is also a good way to tell whether your model is good or not. And it's just not so great here. So what are we going to do? Well, let's try the following thing. As we talked about before, we could do linear regression like we've done so far, but we can fit any number of other models. Here's one model that we can fit. It's called a polynomial regression model. In this case, instead of fitting y equals beta 0 plus beta 1 x, we're going to fit y equals beta 0 plus beta 1 x plus beta 2 x squared plus beta 3 x to the third plus and so on and so forth to some degree. So this is what we're doing here is we're using some neat features of scikit-learn in order to create a pipeline. This pipeline starts by creating polynomial features, a polynomial features object. This polynomial features object, what it does is that it takes data and it generates these polynomial features out of it, x to the first, x to the second, to the third, and so on, all these orders of polynomials. And then this pipeline has both this polynomial features thing, and then it feeds that straight into a linear regression object. So we get together a pipeline that when we make it, say, with degree 10, it does polynomial regression up to degree 10. So that's x1, x2, x3, x to the first, x to the second, and so on until x to the 10th. and then it fits that to our data. So this fits a whole lot better, of course, but it seems to twist itself back and forth quite a bit in order to fit the data, right? It did this whole curve down here and curve up here just so it could hit this outlier point over here. And maybe you're starting to sense that this is a little contrived and not so great. Let me demonstrate to you that this is a problem and what exactly is the problem. And then we'll sort of try to figure out how to solve this problem. So what I'm going to do here now is I'm going to fit the model to one set of data that I've created here. So I've taken and generated from this make xy function up here. Let's imagine that this is some physical process that generates data of this kind. I've generated one sample and I've fit the model to it. And then I'm going to compare that to another instantiation of the same data generating process, another sample from the same physical process. And you can see that now the mean squared error is terrible, 3.76. It's actually higher than fitting a linear regression to the original data. And that's not really great, right? And part of it is like, because the model insisted on going straight through that outlier point over here, it's doing really, really bad up here because this is a huge distance that increases this mean squared error. So, you know, a reasonable thing to do would be to sort of find the right balance. And here's we know that this was generated by a second order polynomial. Indeed, if we do this with a second order polynomial, that seems to fit the data a whole lot better. So, and I think there's a little, if you want to play with this more, there's like a little widget here at the bottom that lets you set the degree and see what happens with various, I think you can change the random seed, so it's kind of fun. So it just demonstrates this again and again. Okay. So what happened here? What did we learn from this little exercise in kind of like fitting different models? I guess one thing that we learned is that, you know, if we thought linear regression was a limited space to work within, in fact, it's a huge space, right? Once you start taking into account, oh, I can put in the transformations on my original features and build these polynomial models, that's kind of infinite. There's lots of things that you can do here. And so the space of possible models that you could learn using machine learning methods is very, very large. That's the first part. The second part here is that we need to be really, really careful about how we do this, because it's easy to fool ourselves that we have the correct model and that we have an accurate model, when in fact, when we take that and just kind of step over to some other data, it performs terribly. And so we need to come up with some ideas about how we're going to avoid this. And the general term for this, what you're seeing here in this is overfitting. In this case, we're overfitting a model with a very large number of degrees of freedom, a very large number of features, or a very large number of parameters to data that has both signal and noise in it. In this case, we're fitting both to the noise in this data as well as to the signal. And if we step over and we look at data that has different noise than the original data, then it won't fit at all anymore. And so this is called overfitting because we're fitting both the signal and the noise in the data. And we'd like to kind of be able to separate those things. Okay, what questions do you have about this notion of overfitting? Yes.
Are there other ways to check like how the model is kind of such variance? Is there like performance to other than the mean like error and I just
I'm smiling a little bit because in my head I'm like, no, there actually isn't. So you could think about other things that you'd like your model to do for you, like sometimes it's preferable that the model also be interpretable in some sense, right? If when we added this, like, let's say that X is something that we understand. It's, I don't know, something in the world, right? Like the velocity of the wind and Y is like the how long it takes for a carrier pigeon to go from here to South Lake Union. Once you start entering X squared, X third, X fourth, like, you know, wind velocity to the 10th degree, it's like, who knows what that is, right? So that's another kind of goal But in principle, when you think about machine learning models, the lower the error is, the higher the R squared is, the better. And we're gonna try to use that as our kind of North Star. And we can talk about, there's more philosophical thinking behind that. Some of the papers that I pointed to earlier about prediction and inference point out that actually if you're looking for anything else in your models, you're kind of making stuff up. This is the only thing we know for sure, is that the error is smaller for this model than for that model, something like that. Okay, so next we're going to think about an approach that will let us empirically and systematically kind of deal with overfitting and create models that we have more confidence in than this model that we just had, where we're like, we're not quite sure. And we've already seen this a little bit, but I'll do this again here so that it's clear. And I'll just tell you up front, the solution to this problem is called cross-validation. The idea behind cross-validation, broadly speaking, is that you would like to fit your model to some data, and then you'd like to evaluate that model on other data from a similar source. And in many data sets, the way to do that is to take the original data and split it up into training and test subsets, such that you can fit the model to some of the data, and you can test it on some other parts of the data that are completely separate from your entire training procedure. So scikit-learn implements, because this procedure of cross-validation is so central to machine learning, because of what we just saw, scikit-learn implements functionality that allows us to do that fairly straightforwardly in a function called train test split. So the way the train test split works is you import it first from the scikit-learn.model selection module, and then you can give it a list of arrays or a sequence of arrays. And what we'll do to each one of these arrays, in this case, I've read again, X all is the 1004 by 1440 data frame of all these brain features, and Y here is the age, 1004 ages of all the abide subjects. And what it does here is that it takes these variables and it splits each one of them based on this variable train size into two components or two variables. It takes each one of them and splits them into two variables. And what's important about this is that it does that row-wise. So on the subjects dimension, remember this is a column vector. So each row in this column vector you can think of as a single subject. And then here, this is a n subjects by n features matrix. So if we take rows, those are subjects. Those are the observations in our data set. And it takes the same subjects from here and from here. That's the important thing, and matches those in the X train and Y train are the same subjects, X test and Y test are the same subjects. So we get, in the training data here, we get 502 of the original 1004. Now, importantly, it does this randomly, so it's not just the top 502 rows, it's some randomly selected 502 rows. But like I said, the important thing is that Y test contains the same rows as X test. They're matched to each other. So we can use that data in order to separately train and test. So here, what we're going to do is we're going to do the linear regression again. We're going to use the training data to fit, and then we're going to do two things. We're going to score both on the training data and on the test data. Let's see how that worked. So this is kind of fun. So remember, this data has a lot of variables in it. So we got, well, maybe you know what happened here. Maybe somebody has some guess. Why are these things so different from each other? One is that one, there's negative. First of all, any ideas about why there's negative variance explained here? Is someone confused by the fact that variance explained is negative? Maybe not. and this thing that's called R squared of all things, like a squared value shouldn't have negative. So if this confused you, that's fair enough. It depends on the definition of the coefficient of determination. The coefficient of determination, when it's positive, it really is the proportion of variance explained. But because a model can actually be arbitrarily bad, I won't write out the equation, but the equation of the coefficient of determination, the numerator is the error of the model, and so the error can grow very, very large. There's in the numerator, there's the error. In the denominator, there's a variance in the data. So if this is smaller than that, then you'll get sort of variance explained. But if it grows without bounds, let's say that the model is just off, completely off, then that number will grow very, very large. And so one way to think about the coefficient of determination is that it's compares the model that you're currently looking at to a baseline model. And that baseline model is a model that says every subject here has the average of the sample. So zero is actually R squared of zero is the performance of the very simple model that says every subject has the average age in this sample. So here we've actually, in the test sample, we found negative, meaning the model is even worse than guessing the average. So how did this come about? That our model is so poor. Remember, this is the same model that we previously fit 5 variables on, and we got a variance explained of 0.2 on the same problem. What is going on here? So let's do something else to try to get to the bottom of this. Let's sample only 200 of these 1,440 variables. So now we do the same thing, except instead of taking all 1,440 columns, we're going to select randomly 200 of the columns and do exactly the same thing. Use the training data to train, use the test data in order to test, and then report to you the R squared in the training sample, which is now lower, 0.79, and the R squared in the test sample, which is now substantially higher, interestingly. So looks like here less is more somehow, and which is interesting. We've created a model that doesn't work as well in our training data, but works a whole lot better in our test data now. That's interesting. And you might already have some intuitions about why this is happening. We'll come back to that also in a little bit. But let's talk a little bit more about kind of mechanical things that we could do in order to do this more systematically. So you might look at this and say, well, you split this up and it's a little bit arbitrarily on like half of the samples in the training, half of the samples in the testing. How do we do this systematically? And one of the systematic ways to do this is called k-fold cross-validation. It's an experimental, you can think of it as experimental technique in machine learning. We take the data, we split it up into k equally sized samples, and then we train on k-1 training folds as the training data and evaluate on the held out test fold. And we repeat this process k times. In this case, k is 10 times. And we use that in order to exhaustively train on every single sample. In fact, in this setting, every single sample in the data set is evaluated for the fit of the model on that sample when that sample is not used to train, right? In this way, we can create, if you look at all these blue things along here, those are an entire prediction on the entire data set that was done for every sample without looking at that sample in the training phase. So it's completely not overfit in this case. So this is the experimental technique, k-fold cross-validation, that we use in order to be a little bit more systematic about this cross-validation approach. And we'll see, we can use this technique in order to start building analysis pipelines or kind of like machine learning, experimental machine learning procedures that help us determine what's a good model for our data. So here we've written out in some detail how you do k-fold cross-validation the explicit way, but I'm actually not going to focus on this too much. This shows in pure Python almost how you would do that. The experimental outcome of this is that you get, instead of getting just one number for training and one number for test, you get, in this case, because k was set to be 5, you get 5 numbers, right? So you could say, like, here I'm getting a first error, a first r squared, a second one, and so on. For every k, for every fold among your 5 folds here, you get a single number for r squared. And then one typical thing to do is to maybe average over that. So in this case, again, this is the model, I believe this is the model that we had that had 200 variables sampled at random from the brain structure matrix, and in training we get about 0.75 r squared, and in test we get something like 0.56. So this is another way of doing this that's a little bit more comprehensive. In this case, this number 0.56 takes into account every single one of the samples in the data set. We haven't split the data set up front into training and test. Instead, every one of the samples in the data appears in the testing data in one of these folds. Okay, and then there's an easy way of doing that. Scikit-learn implements this function called cross-val score. If you create an estimator, the way that we've created them so far, like linear regression here, and you give cross-val score the initialized estimator, some x, some y, and a number that tells you how many folds you want to do, it will run that and it will give you back the test r squares for each one of these folds. So it's, again, very few lines of code in order to do what is a fairly complicated experiment if you had to write it yourself, and no reason to write that yourself anymore. Okay, let me pause here for a little second because I've shown quite a few things here, and see what questions you have about this idea of cross-validation, k-fold cross-validation. Yeah.
Could I use this with something that's like an estimator that is not part of scikit-learn, like a maybe custom function that does something, whatever it is? Can I use that this function?
Yeah, so I think your question is, can I replace this with something else that does something that I've designed? And the answer is yes, you can write your own estimators. It's not very easy. You have to write them according to some very particular specifications so everything works. But you can do that. I can share, I've done that myself. I can share some code that shows what the mechanics are. And then, yeah, you can kind of build some custom model. That might be really interesting for some neuroimaging use cases where, for example, you know that certain variables in the data have to have some relationships between them. So you can insert that as kind of a constraint on how you do things of that sort. You can definitely build your own custom estimator. And also scikit-learn itself, I've shown linear regression a lot, but I'll show soon, I'll show other kinds of estimators that exist there, so that there's a library of estimators that you can use. Yeah.
What decisions go into choosing the number of folds?
Yeah, that's a little tricky. So there are kind of these magic numbers that people like 5 or 10 that seem just kind of reasonable. And you will find that particular number doesn't change it doesn't change a lot about the result ultimately. Ultimately, what you want is a trade-off between the size of the training data and the size of the test data. So if you don't use enough samples in the training data, your model won't be that great because it's not seeing enough data in order to be properly trained. On the other hand, if there's not enough data in the train sample, you might get a lot of variance between different train samples. So these numbers might vary quite a bit if the train sample is really, really small. If you want to read a treatment of this idea that Russ Poldrack wrote a few years ago, he has a blog post about what's called leave one out cross-validation, in which you take every sample, you fit a model for all of the sample except for one, and it just shows that creates a lot of variance in these R squares. You get a lot of variance. So there's kind of like a trade-off between accuracy of the models on the one hand, by having a lot of data, but within pretty reasonable bounds, that number is not going to change a whole. And so long as you're doing this, your estimates of the R squared are not, at least not contaminated by this by overfitting, right? I mean, I kind of pointed to this result up here and said in a little quizzical what's going on here. What really happened here was overfitting to the training data. In fact, in this case, overfitting is complete in the sense that there is more. I pointed that out at the very beginning. There are more features than samples in this case. And so a linear regression model can, in fact, it's kind of mind-boggling, but you can fit, if you have enough dimensions and for a small enough data set, you can fit a linear regression that just passes through every single point in the data. And that's exactly what happened here.
There's a question on Slack.
Oh,
Is
good.
there any clear limitation regarding sample size of the training test data sets?
More is better, I guess. You want to have, depending on the complexity of the model, and we'll get into complexity in a little bit, the model might require a lot of data in order to be properly fit. And then, so if you're splitting your data up a lot and you have only, I don't know, 20 samples in order to fit the model, it won't be very accurate in fitting, in the sense that it will fit to this data and then you'll go to some other data and it'll fit something different. So the parameters will vary a lot between folds. You don't want the parameters to vary a lot between folds. But again, as I said, you want to retain enough data in order to evaluate also in a way that you don't get a lot of variance in the evaluation side. So it's.
There's a follow-up. Is there any kind of power analysis
Oh,
considering that complexity?
I don't know, actually. It's really, this field is very empirical. Part of its charm and also its drawback is that for a lot of these things, there are no closed form solutions because it's really, really empirical and you have to do experiments in order to determine how many samples do I need. And it's pretty typical. We might even have here like these, what are called learning curves, where you vary the number of samples and then just see how accurate, how does the model converge in order to determine that you have enough data. The model converged to a certain R squared, then maybe you have enough data. Yeah. I see hands. Melanie, do you want to ask a question?
Yeah, I'm still struggling a bit to understand why the R squared was negative in that one example.
Yeah, okay, I'll go back to that one. So R squared was negative because this model was so severely overfit to the training data. Because it had so many dimensions, what happened is the model fit a straight, it's not a straight line, it's a hypersurface, a linear hypersurface that passed through every single one of the samples in the training sample. So it's completely overfit to that data. And that took it further away from the test sample than if we had just guessed a very, very simple model that said, let's just guess that everyone in the test sample, their age is the average age, right? The 0 point is a baseline model that is this average Y model, average Y model. So if we had created a different model's average, take the average of Y train and guess that for every one of the Y test, we'd be very close to 0 here. Not quite 0 because their averages might be slightly different, but almost 0. This model, that hypersurface is further away. Its error is larger than the model that guesses the average age for every individual. And in those cases, the model has negative R squared. In fact, you can imagine that you had a model that was so terrible, it would just guess that everybody's age is 20,000, right? That model would be really, really, really far off. Its error would be huge, and its R squared would be even more negative. In fact, this R squared can grow negative without bound. And well, why not 2 million instead of 20,000 or 20 billion and so on? So you can see how the error grows without bound. And as the error grows, this number becomes increasingly negative. Hopefully that answered it.
Yeah, that makes sense. And that happened because you made it fit to every single data point. Okay, got it. Thank you.
Yeah, it's really severely overfit in this case, which we can see because it's 1 in the training sample. It's just completely overfit. It's like one of these polynomial lines that just passes through every single one of the points in the data. Angelina.
Yes, thanks. A fairly related question, and again, maybe I'm just silly and I'm not getting this very well. When you're doing cross-validation, are you taking a completely different data set, like completely unseen? Because I feel like what I struggle to understand is you fit your model, obviously that data has been seen, and then you want to cross-validate, and then you're still separating that into a train and test set. Is that a new data set that you're training on? Is that completely unseen? I'm not sure I got this actually.
Yeah, thanks. That's good for me to make sort of the distinction. What happens inside of cross-val score, in fact, is that in every iteration through, and we're doing 5 iterations through, we split the data like this, right? We have some training folds, all this gray stuff here. The model sees that these training folds and adjusts its parameters to these training folds. And then it tries to predict this left out data that was not seen by this model. So this test fold did not contribute to these parameters. Then we use that model in order to predict this test fold and write down the error, write down the R squared. Now we take the same estimator and we reset it, right? We fit it to a different train data, right? This blue is now the held out, and all these other gray boxes are now the train. So we're retraining it from scratch. We're taking the same estimator, we're resetting it. Now it doesn't have any parameters, and then we're refitting it now to in the second iteration to this second set of training folds. And so now it's predicting again for data that it didn't see at all. This model, so we're refitting the model again, and we're resetting and refitting the model in every iteration of the k-fold cross-validation, such that in every iteration, the test data is really unseen data. So we have k sets of unseen data fit with or predicted with k different models, k different sets of parameters that were kind of refit to every training fold. Does that
Right,
answer your
yeah.
question?
Yeah, thank you.
Okay. I'll skip over this optional thing. I'll just point out that you look at this, if you look at this, you might be really impressed that we can predict the age of the subjects with really what seems like magical accuracy. If you've seen literature on brain age prediction, 0.6 is really, really good. I recommend thinking about that for a little bit and then going to this cross-validation isn't a panacea section. Like, why are we doing so well in this data set, even in cross-validation, just by selecting a random 200 features of the brain? It doesn't make sense. Too good to be true, and indeed, there's a problem. So think about that a little bit, and then come back to cross-validation isn't a panacea. For now, let's move on here. So now we're going to get into model selection. So I've shown you that there's a problem of overfitting, especially in the presence of multiple features and these very high dimensional data sets. And I've shown you that you can use an empirical method, cross-validation, in order to determine that a model is good or a model is bad. The next thing is that kind of immediately springs from that is that you can compare different models to each other also. So you can take 2 models and perform cross-validation with these 2 models and then ask which of these 2 models is better. And that helps us in the sense that we talked about at the beginning. If we want better and better prediction, if we have a lot of models, a lot of options for what model to use, we can run this experiment with many different models and then select the best among them as the model that fits the best and use that model ultimately in order to do whatever it is that we want to do from this whole procedure, right? Like put that into our clinical prediction machine and predicting some clinical condition from brain data or something like that. So that's what we'll get into here, and we'll talk about that. So here I'm importing things, and here I'm loading the data again. So we have features as our kind of X all from before, and we'll talk about this a little bit. I'll introduce sort of a conceptual way of thinking about different models and what they afford us and what they might cost us. By introducing the concepts of bias and variance, and a really important central idea in machine learning, which is the bias variance trade-off. So in the bias variance trade-off, we talk about the fact that you can't have everything. in life. But you can choose judiciously between different evils. So let's talk about this for a second. Assume for a second that we're thinking about a machine learning problem, and let's say that these x's here are different samples. And let's for a second think that all of those samples have the same value. Let's say these are all people with the same age. So in a perfect world, we would be able to get all of them into the bullseye. They would all be sitting right on the bullseye. And that would give us, let's say that the distance from the bullseye, you can think of that as the error in predicting these people's age, right? So there are two different ways in which that this could go wrong. One is by increasing the variance of the prediction. We have different individuals. If we go down in the rows here, from here, this is really great. Low bias and low variance. We're very close to where we want to be. Maybe this is as good as it gets. Small error. But the error can grow large, both by increasing the variance, meaning different individuals who should have the same result get different results. And that increases the error because you can see the total sum of the distances from the bullseye is larger here than here. But there's another way in which we might go wrong, and that's by the introduction of bias. So we could also increase the error by taking the same cluster, and for everyone, we predict very, very similar values, but they're just the wrong values for everyone. And of course, we could do both of those things and get both a high variance and high bias solution, which is down here, which added both of those things. So the idea that I'd like to introduce here, and I'll go into some detail and kind of show it to you, is that there's a way to trade off those things. And in fact, you can find, if you can introduce a little bit of bias into your data. So these things, in fact, empirically, they trade off. And in some cases, you can improve your model performance by reducing the variance through the introduction of some bias. So you insert some bias into your model, or some might say, put in some Bayesian priors into your model. And by introducing this bias, you reduce the variance sufficiently in order to make the total error smaller. Okay, so that's the main idea that I'll try to introduce here in the next 10 minutes and bring us home. I'll skip over this analogy that uses parking lots to go straight to the core of this. So the way that this has been implemented, this kind of introduction of bias at the expense of variance has been introduced into statistics is through a process called regularization. And in order to explain regularization, I will talk about a specific family of algorithms that use regularization that are called penalized regression. So remember at the very start here, when we did linear regression, we used ordinary least squares regression. And ordinary least squares regression, the one that's implemented under the hood in that linear regression estimator, it has a cost function. The cost function is make my errors relative to the data, the squares of those errors as small as possible. That's the cost function that's implemented at the heart of the ordinary least squares or the linear regression object. And this is, we'll call this the residual sum of squares. So residuals are the differences between the model prediction and the actual data, or sum of squares or least squares. And so here, what you see here written in the equation is, if I had fit these betas, the coefficients, and I'd predicted for each one relative to the true, and then sum that over all the observations, and you get kind of the sum of the squared errors across all of the observations. And this is the ordinary least squares. But what people came up with are slight variations on this. So this in fact is the zero bias solution to this problem. It's completely unbiased. That's good. But what people came up with is the idea that let's introduce into this problem a little bit of bias. So what they did is they said, let's create a new cost function. It has this least squares or residual sum of squares criteria, and try to reduce the squared error as much as possible, but add also an additional penalty. In this case, the penalty is the absolute values of the coefficients, right? And in Bayesian terms, this is a sparseness prior. Let's say that we know, we from some guess, we think that as few of the coefficients here should be active. It's not something for this predicting age from brain structure, it's not something that we necessarily know, that maybe only a few areas should be predicting for us. Here, instead, we're saying, well, maybe let's add this kind of bias. We'll say, give me as few of the areas as you can in order to reduce as much as possible the squared errors in your prediction. So you construct this new kind of cost function, and I'll point to this lambda here. Lambda is a hyperparameter that determines how much you balance these two cost functions. You have these squares here, and you have as small as possible the coefficients. This is the absolute value of the coefficients, by the way. The sum of the absolute value of the coefficients in the model should be as small as possible, and they're kind of hyperparameterized. The balance between that is hyperparameters through a parameter lambda. Another form of this, so this is called lasso regression, introduced by Robert Cipriani in the 1990s. But there's actually a much older form of this called ridge regression, also known as Tikhonov regularization, and that one goes back to like the 1920s. And it has a very similar form to this, but instead of penalizing the sum of the absolute value of the coefficients, it penalizes the sum of the squares of the coefficients. So those are very similar to each other. They're both forms of penalized regression. Okay, let's look at the lasso first here. What we're going to do is we're going to create a function that plots what we call the coefficient paths. I'll go ahead and run it, and then I'll sort of show you a graphic here, and it will be a lot more clear. This takes a little while to run because lasso takes a while to run. In this case, what we're doing is we're sampling, again, 200 features. We're doing some scaling on them. We're going to try to predict age. And here is what we see here are the coefficients. So there are 200 coefficients because we've sampled 200 columns from the brain features matrix. And on the x-axis here is this penalty, the what's called lambda here, and for reasons that are not too interesting, is called alpha in scikit-learn. On the left here, we have set that alpha to be a very, very small number. And indeed, the coefficients all have some values. And as we increase the penalty on the absolute value or the sum of the absolute value, the coefficients get smaller and smaller until in the end, when this penalty is very, very large, all the coefficients are equal to 0. So here we've set this penalty so high that it doesn't care about the least squares error at all anymore. It only cares about the values of the coefficients. And it's very easy to solve this because this penalty would go very low when you just set everything to 0. So this is, and in between, there are all kinds of solutions. So this is what we call the coefficient paths. As we go and kind of vary the alpha, the coefficients vary, and somewhere in here, there might be a solution that's a good solution for the problem of sort of that balances variance and bias optimally. And we'll look at how we solve for that. Ridge regression, very similar, but a lot faster. And then has slightly different characteristics. It's not too important. The comparison between this and this are not too important. The principle is the same. Here on the left, where the penalty on the sum of the squares of the coefficients is very small. Here, the penalty is very high, and so they all get crushed down to 0. In between, there's some kind of coefficient paths. Okay. So now I'm going to run all these cells just to get to the point here in the next 5 minutes. And that is that now you're faced with the possibility of many different models, right? Each one of these alpha values represents a different view of the world, a different mixture of your prior, your sparseness prior, and your reliance on the data, or your desire to be unbiased by looking really at the data for the smallest possible error, and this introduction of a bias to push you away from this high variance solution. This reduces the variance necessarily because it kind of constrains you into some corner of the space of all possible models. So that's a way to think about why this reduces the variance. And so we're doing one way to sort of determine how we go about, well, how do we know which of these values of the penalty we should choose? And I'll just answer my own question here, is to go back to the previous notebook that I showed and use cross-validation. So now we can conduct an experiment where we fit all of these models and we perform cross-validation every one of these possible models, selecting the model that minimizes or maximizes the R squared, minimizes the error, or maximizes the R squared in test data. And that's our way to determine which of all these values is the best value. Let's see if that experiment has concluded. There it is. Okay, so this is kind of the punchline of this entire hour and a half. So here we're comparing, we have three curves. One is ordinary least squares. It's linear regression, the linear regression that we saw before. And this is in the test data, so we're doing cross-validation here. The orange line here is lasso on the test data. And sorry, the blue is lasso on the train data. So this is, we're evaluating the model both in the train and the test here. And so what you can see on the train data is you can see the effect of the introduction of this bias. So it stays pretty high, R squared of, I don't know, 0.7 something for a while, and then it starts going down, down, down. As the coefficients go down here, we're starting to ignore the data, and we're starting only to rely on our desire to squish these coefficients down because of this hyperparameter. And so as we go from left to right here, we have to be going down here. This has to go down because it's looking at the training data. And in the training data, the best possible solution is the least squares solution. Has to be. The larger lambda is, the more you're pushing yourself away from the least squares solution. And for the test data, the least squares solution has to be the best solution because it's the one that minimizes the error and maximizes R squared. So this curve has to go down. However, if you look at the test data, what you'll see is that it starts off being as good as ordinary least squares on the test data. And that's because in this case, we are way out here. Lambda is very, very small. And so the parameter that is used, the kind of model parameterization that is used is the ordinary least squares parameterization. We haven't penalized the addition of coefficient values at all. But as we go from left to right here, this model actually improves in performance, reaches some optimal value, and then goes down. Eventually it goes down to 0 as well, and that's because at some point the model is just pushed away, so far away from kind of like the optimal solution that there is essentially down here. In fact, if you can convince yourself later, this model down here is equal to 0 because it's exactly the model that predicts the average. It ignores everything except for the intercept. So it gives you the average, and that's the model that has an R squared of 0. But here what happens is there is actually an optimal value here where this model performs the best on the test data. There is an optimal level of bias introduced into the model that reduces the variance so much that actually the error goes down. So this kind of is the point of all this, was to show that if you use cross-validation to do these kind of empirical experiments on your data, you can find what looks kind of non-intuitive optimal solutions to a variety of problems, in this case, this particular problem. Okay, I'll pause here and see what questions folks have about all that. And we'll quickly towards the end. And if no questions come up right now, they can come up later and we can discuss these things also on Friday. I can go into a lot more elaboration here. I'll just kind of come back full circle to the very beginning. I pointed out when we started that for a lot of the problems that we have a lot of dimensions, and I have this problem that we need to sort of deal with this high dimensionality. And these algorithms are kind of like a classic solution for dealing with high dimensionality. And that's because if you just took the naive approach here, you would be lost. But what these kinds of algorithms do is they push you into a particular corner of the parameter space. They kind of do automatic dimensionality reduction for you as they're fitting. And I'll share a paper that I wrote a few years ago about a variant of ridge regression that actually, I think, if you're interested in all the math of this and you've heard about principal components analysis, ridge regression has a very close mathematical relationship with principal components analysis. And if you enjoy that kind of thing, you can go and look at the math we tried to write in a lot more detail than statisticians usually write when they write equations like every step of the way so that I can convince myself that I understand what's going on. And so if you're interested in that relationship, I can share that paper, and you can see that these things are related. Dimensionality reduction and these approaches are related to each other in some mathematical way. Okay, what questions have come up while I was yammering?
I'll
Yes.
ask one again.
Oh, yeah, there's one here, and then afterwards we'll
Sure.
come back.
Absolutely, yeah.
Yeah, you were.
So this, does this tell us like what features are most important to predict the?
Does it tell us which features are important?
Yes, yeah.
Yeah, so there is a sense in which all of these models do point to importance of various variables. And that's by looking at the coefficient values, right? If you look at these coefficient paths here, like high values here correspond to like big contributions to like so that these models, actually these kind of linear regression or linear-like regression models lend themselves to interpretability. Pretty straightforward. You can just look at the coefficient values. You might want to do things like see what the variance is on the coefficient values across, say, different folds of your data as well, right? What we find with lasso, for example, is that it's, or at least in the use cases where we've used lasso, is that it's depending, you can split up the data depending on the problem that you're doing. You can end up with like very different coefficient values for different folds, all of which are pretty accurate, which is very confusing.
So it's not necessarily the case that a feature that has a high coefficient in the OLS model will survive all the way to the greatest lambda.
That's right. If you look at the coefficient paths here, they're kind of weird. Some of these things go down and then they go up. And so this blue one, for example, it's not as important down here as it is up here, which I
Can we like interpret that anyway? Is that meaningful?
Maybe that's tricky. Interpretability is tricky. And there's a whole lecture to do on interpreting these machine learning models and what it means to interpret it. So in the context of like, we're really adamant that we want the models to be really, first and foremost, accurate. Now we have an accurate model, it's very hard to pull apart. And these models are, like I said, relatively easy to pull apart. The models that Noah is teaching about simultaneously over there are really, really hard. They have millions of parameters. They're like deeply nested inside really complicated computational structures. So if you pull out a parameter from the middle of some neural network and you look at that parameter, it's very hard to say what that's all about. So there's a whole field that's super interesting, and maybe I'll point to some resources about machine learning interpretability, which are very cool. We used some of these in my group's work. We've used some of these methods in order to try to pull apart these kinds of models. Okay, was there a question in Zoom?
Yeah, I wanted to ask one.
Yeah, please.
So if we kind of extrapolate from what we've been talking about so far, would you say that PCA is also a machine learning technique?
Yes, I'll just point out that all these notebooks are on the hub, and there's a sixth one called dimensionality reduction, which puts these things together by doing first the PCA and then the linear regression. So it's a lot more explicit about the dimensionality reduction, but I didn't have time to go into it. But yes, PCA is you can think of it as a machine learning method. It's an unsupervised learning method. The plot that I showed in the beginning with these kind of like, when I said, oh, you could reduce the dimensionality of this because of the correlation, I was effectively doing PCA by eye there.
Right. Yeah. Okay. Thank you.
Okay, and I think maybe we'll stop here. We can come back to these things on Friday at the review sessions, or I'm here all next week as well, so you can catch me. We can talk about this.